Thanks, everybody. I know that everyone is enjoying their lunch, and I'm sorry to interrupt, but I'm the lunchtime entertainment. I'll do what I can. Sometimes it's good to speak quietly and see if people will listen. We'll see. That might not work in this hall. All right. Well, it's a pleasure to be here. For those of you who don't know me, I thought I'd start by asking the question, who am I? It's a question I sometimes ask myself these days, having spent some time running a startup company and then returning to campus. It's a little bit of an existential crisis sometimes. So I went to my Twitter page to see if I could remember who I am. So this is what it says on Twitter: founder and chief strategy officer at Trifacta, Berkeley computer science professor focused on data and computation advisor to tech companies. And as I look at this, these two words are a sort of SIGMOD guy trained as a full stack data person, best effort to describe what I do to the rest of computer science. And I figured data, computation, that's pretty comprehensive. That kind of says it all. I can do anything, right? But actually, that's really not the case. There's a third piece that's missing. And the third ingredient that's really missing from, I think, what amounts to a full computer scientist is a consideration of people. And back in 2010, when I was starting the research projects that I'm going to talk about today, I came to this realization that my training as a systems guy making stuff go fast was kind of not serving me well going forward. With the advent of the web and Moore's law, computing is approximately free. It's absurd how much compute we can get for a small price. Storage is approximately free. Data is abundant. And in this environment, really the problems we should be working on as computer scientists to remove bottlenecks are problems that lie with people. So the research agenda that I was focusing on and have been focusing on since is to dramatically simplify labor-intensive tasks. And I've been doing this in the context, for example, of programming distributed systems, where I think there's an enormous amount of wasted effort in the industry. But today, I want to talk about work in this context in simplifying labor-intensive tasks in the analytic life cycle of data. Okay? So I had a little side project that I started in about 2010 called Data to the People, D to the P. We have a little website, and this is a project where we didn't raise any funds for this research project. We didn't really promote it very much. It was sort of a gathering of like-minded people. So it was a collaboration with the 4 faculty you see there at Berkeley and Stanford, and some graduate students. And we would meet in neutral territory here in San Francisco. So Adobe kindly lent us a conference room where we would meet in San Francisco, and we would talk about things like data visualization and interaction. And one of the sort of central tenets of this sort of portfolio of research that we were developing was that there's a life cycle to analytics. And you can think of this naively as a pipeline. You acquire data, you have to transform the data for use, then you can analyze it, and then perhaps the results of the analysis are visualized, at which point you can either make human decisions or deploy software with automated serving of models, et cetera. And it's nice to view this as a pipeline. Of course, the research communities that I tend to engage with are very narrowly focused at this center of the pipeline, the stage of analysis. And I think for many of us as computer scientists, this is where we are most comfortable, right? But in reality, for users, when you go out in the field and you talk to data scientists and data analysts, they iterate back and forth through these stages very often. And they view this pipeline as their whole job. So for example, when you're visualizing data 4 steps down, you may realize you have the wrong data set and you need to acquire something else. Or you may realize that the data is dirty and you have to go back and do data transformation. Similarly, when you're doing data transformation up at the top, you may decide you need to visualize the outputs to see if they're right. So sort of the back and forth between stages of analysis and acquisition and visualization are by no means linear in practice and are very interrelated. So we set out to do research sort of all along the pipeline, not trying to be comprehensive, but trying to probe into each of these stages and see what we could do as a combination of HCI researchers, my colleagues, and kind of data systems people in my group. And we had, I think, very interesting research, sort of one student or two student projects at each of these stages. It was sort of a portfolio approach to research rather than the big systems approach that I had been used to. And these are examples in each of these buckets. And what happened with this research project, it was perhaps the most successful project I've started in my 20 years at Berkeley. So the first two projects, which I'll talk about today, led to two startup companies, Captricity and Trifacta, which have collectively raised more than $125 million in venture funding and are on their way to growing to be successful independent businesses. The second two projects, MadLib and D3, are widely used open source projects. MadLib, if you don't know, is a machine learning library that runs in parallel with quite a large library of routines in SQL databases. And D3, if you don't know, is perhaps one of the most popular software projects in the world right now. It's in the top 10 in GitHub for data visualization. Right? So these have been very high impact efforts that really grew out of thinking about people up and down the stack rather than necessarily focusing in narrowly on the algorithms for analysis. So in my talk today, time permitting, I will talk about sort of three chapters. The first will be this problem of data acquisition, a very messy problem. Talk about the Shredder research and how it grew into Captricity. Secondly, I'll talk about data wrangling, the problem of taking raw data and getting it refined for analysis, going through the history of two research projects I had in my group and then the founding and growth of Trifacta. And then finally tell you about a third project in open source we're just kicking off at Berkeley with collaborators that is called Ground. Okay, so if this is our life cycle, wow, echoes. We're going to focus first on the top, on data acquisition. And when I started this, it seemed like the most old school, boring problem you could imagine, getting people to fill out forms. All right, and I asked my HCI colleagues, has anybody worked on filling out forms any time in the last 10 years? And they said, no, that's a really boring problem. Nobody would want to work on that. But data entry, as we all know, is a major profession. There are data entry technicians all over the world. All right? It's a terribly poorly served profession by technology, and it's critical in many contexts to acquiring data. I'll mention as an aside that there was other work that we were doing with collaborators at Carnegie Mellon on acquiring data intelligently using automated sensing. And I'm not going to talk about that work today, but there's a separate sort of sensor placement problem in addition to this. So one of the pieces of work I'm very proud of began with my student Kwang Chen. And you'll see Kwang on the right of this picture. Kwang came to Berkeley, and he asked me, sort of with big eyes, if I could help him build a PhD program where he would really help the world and do something interesting with like data integration. And I said, I don't know if I can do that, but maybe we can figure it out together. And what Kwang ended up doing was spending his summers in his first few years at graduate school in villages in Africa, working with healthcare clinics to understand what they were doing and how data and technology could help with rural healthcare in Africa. So in this photo, I believe this is in Tanzania, Kwang is following community health workers as they go off to villages to survey the residents about their health and their compliance with health protocols. For example, do they have mosquito nets and are they using them? Simple questions that can really majorly affect the health of communities. And one of the things that Kwang found when he went to these rural health clinics was the health professionals were interested in the data. They cared. They were spending time building data visualizations and doing data analysis literally by hand. They were getting paper surveys, tallying them, and drawing bar charts like these. Now, you might be surprised to know that actually data gathering and data analysis is not only of interest to these groups, it's required. Many of the funding agencies, like the Gates Foundation, that provide the funds for these health clinics, demand accountability. So what that means is that on the 29th and 30th of every month, they shut down the clinic, and the doctors and nurses get all the paper forms and enter them into Microsoft Access and upload them to the funding agency, never to be used again. The operational day-to-day data of these organizations is locked up in paper. and it doesn't get used in time. So the question is, can we get these people to extract value from their data without waiting for that compute infrastructure and that manual data entry? And so Shredder was a system that Kwang designed with collaborators, myself and others at Berkeley, where we took their paper and using ubiquitous technology, everybody has cell phones in the third world. You mount a cell phone camera on a piece of cardboard, it works as a perfectly serviceable scanner. You scan the paper forms and you upload them to the cloud. Now you have to remember this is very early, this is like 2011. So in the cloud we were using graphical models and structure learning to learn correlations between form fields, and using open source OCR software to scan and get confidences on what the forms in the handwritten fields had, and combining those two models to come up with predictions for what the field reads really were. And then we were using crowdsourcing. Mechanical Turk had really just launched a little bit before that. We were using crowdsourcing to validate the high uncertainty reads from these scans. And with this combination of machine learning and crowdsourcing, we were then sending data back to the endpoint where it could be loaded into a spreadsheet for use. So that was the rough design of Shredder. And in doing this, Kwang also sat in the city and watched the data entry technicians doing their jobs. So when you watch someone type in forms all day, you start to see inefficiencies, but you also see things that they do to make themselves efficient. So for example, the data entry technicians, if they had a series of numbers to enter, would say them out loud because it would help with their short-term buffering as they transferred from paper through their brain to their fingertips to enter the data. And one of Kwang's observations was that when entering all the fields of a form, when they would get to a text field, it would break their short-term memory buffer of numbers that they could enter more efficiently. What Kwang realized was that when you digitize the forms, you can shred them into individual field entries, and instead of having people enter an entire form for a single patient, you could have them enter question 1 across all the patients. And then they would stay in the same data type and have clusters of similar values while they were doing data entry. And we realized that this was very analogous to what we were doing in database systems for compressing columns of data. If you take a column of data in a database, it's all the same data type. It can be very efficiently stored and compressed on disk. And that channel from paper to eyeball to fingers was just the same issue. We wanted to optimize that channel using sort of correlations, using compression, and staying within a data type. And when we thought about that, we realized not only is it good to have people type in numbers, 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 and then characters, 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 but we can also use compression to help. So what does it mean to do compression in a user interface? Well, here's an example that we mocked up, which is you can cluster the scans based on your expectation of what we think that's in them. And then rather than have people do data entry, you can give them a grid of clustered reads, and you can ask them to identify the outliers. And people are quite efficient at this, and in a small number of clicks, identifying the mismatches, you've entered a large volume of data in a batch. Again, think of this as compression through the neural channel from paper, really from scans, to data entry. Okay, so this is a combination of getting the clustering algorithms right, using correlations between fields to do a better job, doing good OCR, and the user experience design to try to facilitate this compressed and type-centric kinds of encodings. Okay. So this was neat, and Kwang finished his PhD, and he set off to change the world and realized from his experience in Africa that it's very difficult to change the world as a nonprofit. And he believed that the best way to do good would be by doing well. That is to say, to start a viable business in the first world and use that to fund his .org for rural and third world applications. So Captricity was the company he founded, captricity.com, and they found a very good business in the insurance industry where paper is regulated and required, and there's enormous backlogs as well. So let me give you an example from Captricity of one of the things that they've done with one of the major insurance companies that you've heard of. And it's analytics enablement for life insurance. Cause of death data is a great predictor of fraud in life insurance claims. But there's not a very good training set of cause of death data because it's all on paper. These are county records and state records, and they're in many different forms and templates. And so they went into this insurer, and they were able, using their software and the crowd assist, to efficiently digitize decades of death certificates and enable the fraud detection for this life insurance to get much better. So that's one concrete example where even in the sort of developed world, there's still a lot of paper. And I think as we come up to the elections, there will be more discussion of the benefits of paper versus digital data entry over the next few months. But Kwang also founded Captricity.org, which is a nonprofit. And they're doing things still all over the world to help with data entry. This example is in Botswana, where there's an organization to reach out to young people. There's a disturbing trend in which wealthier, older people will become quote-unquote sugar daddies, that's the name of the program, to young, susceptible people, and pay them with gifts and cash to enter into romantic relationships. So the goal of the Young Love program is to sensitize children to the risks, the health risks, and the safety risks of getting involved in these relationships. And one of the things they were doing to see how this program was working was they were going to schools, and they were reaching out to the students to do surveys in class, because that was a place where you could get groups of young people at once and assess how the program was doing. And of course, that was all done on paper. And so Captricity was brought in to bring those paper forms and analyze them and allow this nonprofit to be able to assess and improve the quality of information and outreach. All right, so those are two examples, one commercial, one nonprofit, of the way that data entry can really make a big difference. So some lessons as researchers or engineers. Two things. I think when you take problems from the field, when you step out of the halls of your internet company or your university and you go in the field and talk to users, you get some interesting problems that you might not have thought were interesting. And take that and multiply it, obviously, by the innovative ideas that people in this room would have. And you can have enormous impact, much bigger than if you only did one of these things. It's really a multiplicative effect. A second surprising result I found from this work was this idea that kind of core systems ideas from my world, things like data compression and clustering and instruction locality, had relevance to user experience and user interaction problems. And the idea that systems people could walk into a human-computer interaction lab and contribute to the design in meaningful ways toward efficiency was very heartening to me, and I think helped build good bridges in my collaborative group. And then finally, and I think for this audience this is a point worth mentioning, crowdsourcing is a beginning of that kind of relationship between robots and people, right? It's humans as API to do an algorithmic step. And so we got to see that here. But what I want to emphasize is that this challenge of optimizing human microtasks is the tiniest taste of how humans and computers can interact. It's really very shallow. And in the next project, what we'll talk about more is how do you meaningfully help people in much richer ways to interact with computation. So it's nice to work on things like crowdsourcing. It should make you feel like you're working with people, but I'd like to encourage the community to reach deeper into this combination of people and machines. Okay, so we talked a little bit about chapter 1 about acquisition. Next, I'd like to talk about transformation. So this is an area that's near and dear to my heart because I've put many years into it now, in founding Trifacta, running it as CEO for 2 years, and then staying very involved while also being at Berkeley. And when we were designing Trifacta, we knew that data manipulation, data transformation, is a deeply human-centric task. Maybe for those of you who are paying attention, raise your hand if you do a fair bit of data analysis of your own. So you know firsthand, or maybe secondhand, how much time is spent munging your data, wrangling your data. And you probably also know firsthand that when you get a data set, even if someone else has prepared it, that doesn't mean it's ready for your use case or for you, right? And so we needed to design this for people, not necessarily highly technical people like us, by the way. Design this for the people who understood the data and how it was being used. And key to that design was that we were designing it for humans, not for science fiction. All right, and so I don't know if you've seen these two movies. Spike Jonze's movie Her is about a very intimate and quiet and personal and very human interaction with computation. And it's in major contrast to Minority Report, which is really a sci-fi movie about gadgets and about the impact of algorithms sort of on us in a fabulous kind of way. You'll notice that the primary interface that Tom Cruise is using there, you can't do this for very long. Your arms get tired. This is a terrible user interface, okay? So you got to think about simple things like ergonomics, but you also have to think about how people do their work. So we were very much inspired when we brought in our UX team at Trifacta to worry about designing for humans. Even rolling back to campus, though, how do you go about designing for humans? Well, maybe a good thing to do would be to talk to some, right? So we began our work, actually, by asking the question, where does the time really go in that pipeline? What's the most important problem? And this is maybe a bit of a cliche by now, but what we did hear back is 50 to 80% of the time in data analysis projects are spent preparing the data. And DJ Patil, who used to run the data science group at LinkedIn and is now the data scientist in the office of the President Obama's office, wrote a book in which he talked about that from his experience at LinkedIn. Separately, we went off and did a user study paper where we validated this. Actually, we discovered this point without trying to validate it in talking to enterprise data analysts. This paper I very much encourage you to read. Most computer scientists don't go off and read papers like this, much less write them, and I learned a ton watching my colleagues drive this process. We interviewed 35 analysts from 25 different companies in a wide variety of industry sectors with a wide variety of skill sets, different titles. Some of them were nuts and bolts engineers, some were data scientists, some were managers. And we learned many things and summarized them in tables and so on. But I want to share a couple anecdotes with you that I think are very telling. So this is a quote from a data scientist at a digital marketing company, a very technical person, probably akin to many of us in this room. I spend more than half of my time integrating, cleansing, and transforming data without doing any actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. All right, so maybe this is not that surprising. It speaks to the incredible friction between what we want to do and what we're able to do with data. Just getting started is so slow. But the second thing he said was really what I think was most fascinating. Most of the time, once you transform the data, the insights can be scarily obvious. And I think, again, many of us have had this experience. When you figure out your features, when you figure out your level of aggregation that you need, and you got all your outliers cleaned up, maybe you need to run an algorithm, but maybe you can just see what's going on visually, right? And this speaks to the fact that, hey, guess what? If we could just enable the people who understand the data and understand the domain, if we could empower them to do their own data transformation, they don't need to understand sophisticated algorithms. They can do quite a lot of data analysis on their own. So there's a huge lost potential for people to do real high-value data analysis. All right, a second quote, and this one comes from Monica Rogati, who is also part of that LinkedIn data science team, later on ran data science at Jawbone. And Monica said, it's easy to just think you know what you're doing and not look at data at every intermediary step. And analysis, and I can't overemphasize this point to those of you who are graduate students and haven't been out in the field, an analysis has 30 different steps. So the paper that you just presented might be one of them, which would be great. Okay, but remember that it's part of a long chain of work that a real person's going to do in the real world. An analysis has 30 different steps. It's tempting to just do this, then that, and then this. You have no idea in which ways you're wrong and what data is wrong. And so Monica's point was that you really need to get your eyeballs on the data every step of the way and be interacting with that data in an intuitive way as you go. Right? A good data scientist knows that. And of course, this has not been lost on the Twitter sphere. In data science, says Big Data Borat, 80% of time spent prepare data, 20% of time spent complain about need for prepared data. So it's become a meme, but it's certainly true. Why is it such a big deal right now? Well, think about what's changed in the last 5 to 10 years, in part thanks to the technologies we've been building. We have more and more sources of data. and our data sources become more and more complex. We don't just have business data anymore. We have machine-generated data, sort of IoT data. We have log data from software, web logs, user interactions, and on and on. So the sources of complexity are only growing. And interestingly, our data products on the right-hand side, we're striving to make them simpler and more consumable by regular people. So algorithms like fraud detection, or simple data visualizations like we see in newspapers or on websites, or recommenders, these are all things that are intended for mass consumption. So we're trying to make the world more complex on the data side and make it more rich yet more consumable on the product side. And in between are the poor schmoes who have to transform the data, the many sources to the many targets. Traditionally, this is done in the IT department of a large corporation by people who really want to be like fiddling around with system configuration for their cluster. They don't want to be doing data prep. It is not what they went to take the job to do. And what they find is that they're being asked to write transformation scripts because data transformation isn't a one algorithm problem. Every case is a little bit different, and it's death by 1,000 cuts. But the way to think about it as computer scientists is what it really is a programming problem. These poor folks are writing one script after another, trying to transform this data. And we have to think about data cleaning, in essence, as a code generation problem, a programming problem, okay? So what's really involved? Well, one thing is, of course, there's nice high-level languages like Python and Bash and Ruby to help us go on the left from data and write code and compile it and run it and generate output on the right. Better yet, you can use a domain-specific language for data transformation, of which there are many. Going back in the SAS tool, there's a language called DataStep. How many people have used DataStep in this room? Not too many. It's not a big SAS crowd at KDD, I expect, so it's pretty old school. There's research, from the early 2000s on Ajax, and then more recently there's open source tools like Pandas and dplyr. How many of you have used Pandas or dplyr? I would expect many more. Yeah, good. And then, we have a language in our tool called Wrangle. The guy who wrote Pandas, Wes McKinney, has a new language that looks much more like Wrangle called Ibis, and so on. So a domain-specific language can certainly help, and I encourage you to use one. They're easier to read, they're easier to debug because they are domain-specific. And that's nice, but what's actually nicer, as Monica Rogati talked about, is to have your eyeballs on the data. So back in 2001, I worked on this problem with a student of mine named Vijay Shankar Raman, who now heads up a team at IBM. He built a tool called Potter's Wheel. And what Potter's Wheel was a grid or spreadsheet interface to the data that would work on data of any scale. So data would stream by, and it would continue to pull stratified samples, essentially, of the data into a spreadsheet interface. And then he had a DSL, a data domain-specific language for data transformation that was visual. Every verb in the language had a corresponding output in the data that you could understand and see. So that every time you pulled down a menu item, you could see what it would do to the data. But unlike a spreadsheet where you actually mutate the data, all this was doing was compiling a list of the commands that you had chosen. So it was actually gathering up a script of your work, optimizing it under the covers, and executing it on screen, okay? Which meant we had full data lineage of what you'd done to the data. You could redo and undo. You could save the script in the output and turn it into an automatable piece of code. And this was nice, okay? And there's been a lot of tools, I would say, in the last couple of years commercially that are essentially delivering this functionality. So it's worth having a look and understanding what this is trying to do, this tool. Really what it's doing, conceptually, is it's lifting you from the domain of languages, where you take data and you transform it to output in a domain-specific language in text. It's lifting you into a visual domain. Lifting in the programming languages sense, in the math sense, into a different domain in which you have a different language to operate with. So the data is transformed into a visualization. And never forget that a table view with a scroll bar is a visualization and a very useful one. So lifting you into a visualization, allowing you to interact visually with the data in some way, getting a visual result, and then taking those behaviors, those interactions, and transforming them, compiling them back down to generate output in the original domain. So it's very much lifting into another language. The languages may not be isomorphic. Very often in the visual domain, you don't have access to the full power of the underlying language, but it's much more intuitive for users. And this is nice. This is roughly also what charting packages do, right? Visual charting packages like Tableau. So this is helpful. But what we found was that it didn't really help users that much because they still had to specify step by step, whether it was visual or whether it was textual, all the things they wanted to do to their data. And very often they didn't know how to say those things or they didn't know what to say. So to emphasize this, problem number one is that problem we know about where your software doesn't understand what you're trying to do. Very frustrating, particularly to non-technical users. But let's not also forget problem number two, which is that the user actually doesn't always know what they want to do. And if you've ever worked with a messy data set, I'm sure you'll sympathize. You crack it open and you go, oh my God, I don't know what's in here. Let's, well, that looks interesting. Let's pull that out. No, that wasn't what I wanted, right? So you don't know what you want to do at first either. So there's got to be some kind of give and take between you and your computational tools to move you along the path to progress. And if the tool just sits there like a lump and waits for you to tell it exactly what to do, that can be very unhelpful. We're seeing hints of more intelligent interfaces in things we do every day. Web search, for example, at Google, some 5 years ago, I think, maybe 6 by now, they released this sort of type ahead feature, intelligent search, I think they called it, predictive search, where you start typing and it finishes your typing for you. So it gives you a ranked list of likely things you're going to type, and importantly, it gives you a preview of the outcomes of the top-ranked thing, so you can get a sense of whether you're moving in the right direction. And it's very fluid and very natural, and you almost forget it's there. But it's a kind of different experience than the traditional, I tell the computer to do something, and it does it for me. In some sense, it's second-guessing you. And in another sense, it's helping you do things you weren't sure what you wanted to do. So the type ahead works, of course, because it uses context. It knows about you. It knows about things you've recently searched. And of course, it uses the corpus to predict your search terms and preview those results. All right, so what's going on in this search query autocomplete is it's a little bit less linear. You type in the text box, and you get some response, so it knows that you've typed. But it also goes ahead and does prediction, and it gives you a set of suggestions. And from those suggestions, you pick one, and that's your query, right? So we like to call this, and you iterate, obviously. I like to call this the guide-decide interaction loop. Rather than the command-response interaction loop that we're used to, guide and decide involves you in a probabilistic space with the algorithm, which is searching through all the things you might do and ranking them. The thing with text search that makes it easy, which is a good place to start, is that the input and output domains are the same. You type in a search term, it suggests a search term, right? So is there something we can do when the input-output relationships are more complex? And so the research project we did in 2011, Data Wrangler, which is still available at Stanford for you to play with, was a step to take that Potter's Wheel tool and move it forward into this kind of a user experience. It did an automatic inference of your transforms. When you would gesture at the data, it would guess what you were trying to do. And I'll show you a demo of this briefly. It had a predictive preview of the results, so you could see if you did this thing that I'm suggesting, what would you get? And like Potter's Wheel, it kept a history, but in this case, it was interactive. You could change the steps you did previously in the tool and see how your edits would transform the outputs. And of course, this time around, I was working with proper HCI researchers, so we did user studies to validate that what we were doing made sense. And really what this did is it took data transformation and it turned it on its head, kind of flipped the paradigm. So traditionally, when we clean data, and I've watched data scientists who do this for a living, which I don't, do this, it kind of works like this. You author a data transformation script in Python or something like that, and then you grab a sample of the data you really care about, so that you can move quickly and work on small data. You run your script on that sample, and then in the visual domain, you assess your results. So you do a chart, right? You say, wow, that didn't clean up my data the way I wanted. I'll start over and write some more code. So the user lives in the world of code and data, and the computation helps by showing you visualizations. we're going to flip this around. We're going to put the user in the visual domain, and we're going to auto-generate the code. So the way this works is software can pull a sample for you. If you have a terabyte in Hadoop, we can pull a sample for you. We can pull the head of the file just to get you some structural information. And we can do a reservoir sample or something to get you more data from the file, maybe even stratify it based on some features. So you get a sample of your data for free, and we visualize it right away. And maybe the visualization you get is garbage because we don't know what the data is. That's fine. We all do that. We open the data in a text editor. We're used to seeing garbage as our first hit. That's OK, because we can sort of peek around in the garbage and see what we can find. And you can do things like gesture. That character over there is interesting to me. And when you gesture at the data, that's the point where inference comes in. And machine learning algorithms can predict statements in the domain-specific language that would be likely, given the features in the data that you've highlighted and the data set itself, and perhaps a learned corpus of user behavior, can predict statements in the language that you might like to deal with the data that you've highlighted. And push it back up into the visual domain as a data preview to show you the outputs, so that if you select the characters here, you'll get a column of numbers with this distribution. Does that look right? So this interaction, very visual, very effortless, is driven by keeping the user in the visual domain and using computation for what we're actually interested in doing, which is intelligent algorithms at the computational domain to save work for users. And again, this is the guide decide loop. Guiding is gesturing at data, and the deciding is looking at suggestions for transforms from the data transformation code. So we call this predictive interaction, and it's a bit of a variation or a combination of what we've seen before. We have a domain-specific language. That is the domain in which we search for expressions. It takes data to output. We lift into the visual domain and show data to the user. The user interacts with the data, gets a response for their interaction, and a set of predictions. For those predictions of statements in the language, we actually code gen them, run them, and get the visual outputs to present to the user, at which point they can choose the outcomes that they like, possibly annotated with the code, to pick the result they want and ground it back down. So that's the model, sort of the user model and the algorithmic model for how predictive interaction works. And it's fairly general. You can use this in lots of contexts, not just data transformation. So again, guide and decide. All right, and with that, I want to show you a little demo of this in a commercial tool in Trifacta. And I'll take a minute and just look at some data with you if you'll entertain that for a couple minutes. So let's open up the Trifacta tool. Last night, I spent some time gathering tweets from Hillary Clinton and Donald Trump. I don't know, how many of you saw the news last week about Donald Trump's tweets and his devices? Did you see that? It was a really awesome blog in which they analyzed Donald Trump's tweets based on things like what device type were they coming from, what client ID did they have, what time of day did they come from, and then some very lightweight sentiment analysis where really all they did was they joined the words in the tweets with a list of tagged words in their sentiments. It was really just simple data wrangling. And it was essentially exploratory data analysis a la Tukey. Very interesting. And I said, my God, you can do almost all of this visually on Trifacta. So we don't have time to do all the steps, but I'll show you a flavor of it. So let's go ahead and load Donald Trump's tweets into Trifacta. Before I do that, for those of you that have not had the pleasure, here is the outcome of the Twitter API. You can get 3,200 tweets from any user, and it comes out in JSON, and it kind of looks like this. And again, on first touch, you're like, wow, that's a little bit hairy. I'm not sure what's in there. So let's load that up into Trifacta. And I'd also like you to imagine that you're not that data scientist using Python who wrote that blog post. You're like a normal person who uses a spreadsheet. Okay, you're a data analyst. All right. So we're going to create a data set in Trifacta. We'll load up Donald Trump's tweets here from the file system. Yeah. So we'll try this. All right, we're going to open this data set in Trifacta. And the first thing it's going to do is something automated. It's going to unnest the JSON at one level and present us with a tabular visualization of the data. And for each column, it's going to show us a distribution to the best of its ability by guessing at the data types and building bar charts and histograms as appropriate. And you'll see that with this data, those visualizations at first are not interesting because we haven't pulled out the good stuff yet, right? But at least we can get a look at the data. There's the keys, contributors, truncated text, et cetera. Let's go to a list of all those attributes. And I'm very quickly going to pull out the ones I'm interested in. The text of the tweet, the source of the tweet, what client it was in, the user, and perhaps what time this tweet was created. And we'll drop the other attributes for now. Oops, I did the wrong thing, but it's all a script, so we just undo it. And all is well. Text, source, user, and created at. And this time we'll say drop others. There we go. All right, so now we've got sort of 4 attributes that we're interested in. And you can look at them. The sources actually, they're messy, but there's only 3 possible data sources. So that's good. That's probably easy to clean up. And when we eyeball them, they look about right. The created at data timestamp looks OK. And let's just pull out the time of day from this, all right? And so here's my first example of what we call predictive interaction. Here's the time in that timestamp. And when I highlight it, I'm going to get a set of suggestions from Trifacta at the bottom of things I might want to do with the data and little visualizations of what I would get if I chose them. And for the one I'm currently hovering on, I also get a view in the upper table. So extracting things that match the pattern time is giving me a distribution of times here that looks quite reasonable. And this does make sense as what I'm trying to do with this work, as opposed to, say, replacing the time with something or counting the occurrence of timestamps. What I want to do is extract the time. So I'll add that to a little script I'm building on the right-hand side. The first few steps were filled in by Trifacta for me, and I'm now adding steps. So now I've got a time column. We can rename it to be time. All right, and maybe we'll drop this created at column because we're only interested in the time of day information. Another thing we might see here is that the user information is actually deeply nested. So I don't know if you can see this. Let me see if I can zoom in for you here. But this is a map field, right? So this field is a nested JSON map, and we're going to unnest it. And the way we'll do that is let's look at one example of this field. So we'll zoom in again here. These are the different subfields that are contained, right? And we can pick one of them like screen name, and that's our friend real Donald Trump. And when we do that, zooming back out, we get suggestions for what we're trying to do. Perhaps what we're trying to do is extract the string screen name. But that would give us a column of values that all say screen name, which is not what we want, all right? Or perhaps what we're trying to do is unnest the attribute screen name, and that we get a column named screen name and values real Donald Trump. So that's what we want. We'll add it to our script. We'll close that, and we've got our screen names. At this point, we might want to merge in the Hillary Clinton data. I'll do that very quickly. I prepared this already, so I will save you the trouble of watching me do this twice. It finds the columns that line up. We add it to the script. And now we've got Clinton and Trump data. And everything in this interface is amenable to predictive interaction. So if I click on a bar in a bar chart, so let me zoom in again for you. You can see in the screen name field, we have real Donald Trump and Hillary Clinton now. If I click on Hillary Clinton, a bunch of things happen. First of all, I get predictions for what I might want to do if all I'm interested in is Hillary Clinton. Maybe I want to keep just the rows with Hillary Clinton or delete the rows with Hillary Clinton or set their names to something else. But we also see in these visualizations, we see brushing and linking. That is to say, we see correlations. So I'll do this one more time. Watch the source field here. When I click on Hillary Clinton, you'll see that 2 of the sources are more common for her. This one and this one. And when I click on Donald Trump, 2 different sources are more common. So they're using different clients. And we might want to make this a little easier to read so we can pull out, the client names from the insides of these URLs. And this might take a little poking around for the right suggestion. With a few tries, we'll probably get it right. I like that one. After less than and before, after greater than and before less than. That's got all 4 of our values. I'll add that to our script. And so let's do this again. Click on real Donald Trump, and you get, you're going to get iPhone and Android. We got to pull this stuff off too. So let's quickly just remove this stuff. I don't like that. Please replace it with nothing. Thank you. And you can see how quick all this is, right? You can see that no programming, no regular expressions. So Trump is Android and iPhone. Clinton is TweetDeck, all right? Now, I'm not going to take the time now, but what the blog post did is it zoomed in and it looked at correlations between time of day and device. And if you've read the post, you know that there's an iPhone in the Donald Trump account that tends to tweet in the evenings, and Android tends to tweet in the daytimes. And then the next thing you do is you break the tweets into terms, you join the terms with this simple sentiment dictionary, and you find that all the cranky stuff happens on the iPhone in the evenings, and all the nice tweets about thank you, Cleveland, happen in the daytime. And so very clearly, the candidate himself is on his iPhone in the evenings, and the campaign is using an Android device during the day. So this is all doable graphically thanks to stuff like predictive interaction. Even the correlations can be seen very easily. So this gives you a flavor of how predictive interaction can help enormously, both in the efficiency of people like us in keeping our eyeballs on data as we're going through the steps, and in the ability of non-technical people to come to the table and work with data and do things that don't require sophisticated algorithmics, but do require mucking around inside data sets. So Trifacta obviously has been commercializing this software now for 4 years. We have customers in a wide range of industries: healthcare, consumer packaged goods, financial services, pharma, high tech, on and on. So here's some examples. And one use case that's very similar to the silly Trump stuff that I just showed you is in customer 360, or really understanding your customer. So the Royal Bank of Scotland uses Trifacta aggressively, and their first use case was in taking web chat logs from their customers. Upon a time, we used to walk into a bank branch and the teller knew us and they would make sure we were happy. Banks have a very hard time with customer loyalty now, and the way that they can help is by understanding customer interactions, namely things that happen digitally, like web chat. And so within a few months, they went from looking at a small percentage of their web chats to looking at all of them. And this is being done in the line of business, in the customer satisfaction department. Okay? So big change in the way they were able to do their business. Orders of magnitude improvements in human efficiency. Okay, so some lessons from this piece, from this chapter of the talk. Predictive interaction is a motif, a design motif, that involves algorithms that I think this community could really enjoy working on. How do we make interfaces that allow people to guide and then have the computer make suggestions and then allow people to decide? This is actually how we interact with much technology. There's an underspecified UI, things happen, and we like it or we don't like it. Okay? So there's algorithmics around that, there's design around that, there's HCI. One thing I'll point out under the covers is that having this domain-specific language is extremely useful because it does two things. First of all, it allows you to take the results of this experience and compile it to multiple platforms. So Trifacta, for example, currently runs on, I think, 4 different query engines, 2 of which we use internally, 2 of which are for scale. So Hadoop and Spark and a JavaScript engine and a C++ engine. And we compile to all of those engines from the same domain-specific language generated by the UI. So that's nice. It gives you portability. But think about it as a machine learning person. The predictions we want to make here, what do you want to do with data? Well, lots of things. I don't know. What can I write in Python? I can write anything in Python. I would hate to write a predictive algorithm that generates lines of Python based on user intent at a UI. It's too big a scope of search. When you get to a domain-specific language, now you have a nice, tight domain to search where you have a chance of actually making meaningful predictions and gathering meaningful training data to drive those predictions. So Trifacta Wrangler is a free tool you can download and use, and I'll thank you for using it. We will watch things like sequences of transform verbs that you use to try to improve our predictive models and do a better job over time. And we can do that because there's something like 14 verbs in the language, and then regular expression learning models over patterns, and data type induction models. And they're very factored and segmented models based on this domain-specific language. So the design of the right language and picking the right domain of features to predict is key to making this user experience possible. Finally, the notion that you're continuously profiling. The data visualization is not an end goal. Data visualization is an assist to the designer at all stages. I think should be baked into many more of our tools. It's surprisingly inconvenient in our favorite notebooks and workbooks and and other tools that we use as data science, it's surprisingly inconvenient to get a visual profile of all the columns of our data, or all the features of our data. You can draw a plot, sure, but you have to kind of do it proactively. You have to choose what you're going to plot. It would be really nice to have more of the kind of immersiveness that's built into Trifacta in more of our open source data science tools. Now, Wrangler is a tool that you can use for free, and Trifacta is free. But I think we haven't been thinking about this enough as a community, and we could think more. So the data profile also, as you saw, is an interface. Bar charts can be interface. Scatter plots can be interface to specify user intent. Users want to point at the data. OK, life cycle. So we've seen this life cycle. And what became clear to me working in the field with partners at Trifacta, so the engine vendors, the analysis vendors, the visualization vendors, is that those feedback loops are not well supported by software. And it's very hard to understand the context that the data scientist lives in as you transition across the tools. Right? You go from your horrible plumbing like Kafka to get the data in the system, and then you use something like Trifacta to transform it, and then maybe you run it through R to do some analysis, and then maybe you use Tableau to visualize it. None of these tools have anywhere to talk to each other, even if they want to. So we partner with all of these players, and there's no open source big data software to put the metadata. There's nothing. There's no place to put the context. And so it became clear to me that not only was this a crisis in our software stack, that we were desperately missing the context to knit these pieces together, it was also a research opportunity to do something different and more holistic than we're used to doing as individual data scientists on a pipeline. And so I'm starting an open source project hosted at Berkeley called Ground. And I want to spend the third chapter of this talk talking about Ground, which is trying to provide a broader context for big data and analytics. And Ground is a collaboration between a bunch of players who've come together around this vendor-neutral open source project at Berkeley. Sorry for the animations. OK, so one of the things to understand the opportunity here is to ask what changed when we went from traditional data warehousing to big data. And I would argue you've heard the 3 V's and all this nonsense, but I think the biggest things that you want to focus on are the shifts in user behavior and the shifts in the underlying tech stack. So let's quickly look at both of them. In the user behavior, what we have now are organizations that are fully data-driven. Data does not only exist in IT. In fact, data has escaped IT. So the IT department in big organizations either doesn't control data anymore or is losing control or happily letting go of control. Gartner predicted some years ago that by 2017, the marketing departments would spend more on tech than IT. So marketing is where this first happened. But by now, with things like IoT, it's happening in product groups as well. The core business, their core products are very data-driven. So if you talk to GE on their wind farms, the blades are talking to each other about wind shear and adjusting their behaviors based on real-time data. And again, Gartner now has updated their things to say that by 2020, 90% of IT's budget will be controlled outside of IT. So even if IT is managing it, the lines of business are dictating what the data is and how to use it. Interesting. This is very different than the Sigmod-style database accounting that we used to do in the 90s. All right? Really, the sort of analytical view of data and the value of data is a big shift in these businesses. And what it means is that there's many more use cases in an organization for data than there used to be. There's many more constituencies in the organization who care about the data and the analysis. They have different incentive structures. They're paid for success in different ways. So they will want to torture the data at different timescales and at different levels of depth very differently. And that means there's many contexts in which this data is going to get used. And we have no software that is accounting for this changing reality of usage. All right, what about the shift in technology? We went from data warehouses to data lakes, right? So data lakes, what's in the data lake? Raw data, not cooked data, right? So raw data is in there, that's great, because it's easy to capture the data then. We don't need to fit a schema, and it encourages exploration. That's all lovely. But now you've got these crazy data sets in the data lake, and you get questions like, well, what does this data mean? Right? And the answers to those questions typically are subjective. It depends on the context in which you're going to use this data. What do the web chats mean for the Royal Bank of Scotland? They mean lots of things. What are you trying to achieve, right? So it really depends on your analysis what the data means. And that's very different from our traditional model if there's a data model or even a statistical model. It's different for every use case. Same data sometimes, often. Okay, so there's many scripts to convert that data into the use case where it's going to get used. There's many models, both data models in the classical sense and statistical models in the statistics sense. There's many different applications being built on this data, and again, many contexts for the data. So both top-down from usage patterns and bottom-up from technology trends, context is becoming much more varied in these organizations. So the meaning and the value of data depends desperately on understanding this context. And we can break it, I think, into three categories. There's application context. There's really the what does it mean. So the truth of data is subjective. Different people and different groups with different incentives will have different views of the data. So they all have their own data models, their own data transformation scripts, their own training data, their own statistical models, et cetera. There's also behavioral context. How did this data get used? If we understand something about the usage patterns of a data set, how often it's used, what kinds of scripts are run on it, what features tend to get pulled out, what models tend to get built, we can understand something about how that data is meaningful to the organization today. Meaning comes from behavior to a large degree in these contexts. The only people who really understand the meaning are the analysts. And the only thing they'll do to tell you what the data means to them is use it. Right? They're going to do their job, they're going to build their model, and they're going to get their application running. How are you going to extract that meaning from them? By watching their behavior. And we already do this for so many domains. We're trying to understand user behavior for people clicking things on the web. We're trying to understand user behavior for people wandering around in the world or driving. Why aren't we trying to understand the behavior of ourselves, analyzing data? We're not capturing our own data exhaust, right? From our own activities. So behavioral context on data is very important. And then finally, historical context is critical. Things change. And as people in this room probably know well, if you're doing something like experimental design or reproducibility, you want to go back to the data and the code from last week and see what was going on then and possibly compare it to the data and the code now, right? And you want everything from last week to be there. You want the same training data, the same model parameters, the same code, and you want to be able to move back and forth in time. You also want to be able to do longitudinal analysis. How did this behave over time? Who's been most actively massaging these scripts? Who's the expert on this topic and during what periods of the year? So really we want the historical context because things change. I want to keep all of this stuff, all right? Which is a lot more than the metadata in your relational database, right? This is really a much bigger context of thinking about analytics. And without belaboring the point, I think if you build these things, you can do a lot of useful features in the tools for the analysts as well. So I'm not going to go through all this, but you can imagine how in pipelines you would use knowledge of context to help users understand things like, here's one. While you're looking at a data set, it might say, hey, while you're looking at this data set, you might want to compare it to last year. I have last year's data set over here. Would you like to look at it? So recommender systems targeted at data scientists, right? Or here's another example, curation tips. Did you know that the logistics staff is checking the weather data the first Monday of every month? And typically it's 2 weeks old because you're not buying it at the right time of month. Maybe you should change the buy period. So it's supply chain management for data analysts, right? Proactive impact analysis. The Twitter analysis script changed. You should check the boss's dashboard, which is downstream of that analysis, to make sure it's not broken, or the boss might make some crazy decisions. Right? These are all things we could do if only we had the information, and if we set our skills as a community of data analysts upon our own processes. So Ground is an effort to provide this big context and set people like you loose to innovate on top of it. And I won't have enough time to talk about the details of Ground today. I'll just urge you to come to our website, ground-context.org. Okay, so to sum up, I kind of feel like there's three pieces, going back to the very beginning of the talk: people, data, and computation. And we have to think about all of them. And maybe three themes to take out of the talk. Dealing with data involves much more than algorithms. And I'm continually inspired by people like my student Kwang, who go out into the real world to look for high-impact problems. Secondarily, this human component that people like me, trained as systems folk and algorithms folk, and people probably at KDD trained as algorithms and scale folk and machine learning folk, we have a tendency to forget the human component. I think that's where most of the white space is. And that's why I started my company there. I think it's very hard to make a difference building a faster mousetrap or a mousetrap with a 5% greater yield unless you're at gigantic volume. It makes sense to do that at Google. It's not clear to me that it changes the world outside places like that, or that it's a good opportunity for an entrepreneur. Whereas facing human inefficiencies is a huge tech white space. We do so little there, and there's so much opportunity to do clever things, write papers, build products, experiment with prototypes, et cetera. And then lastly, if you walk away with one thing from the forward-looking agenda, this idea of context is really key for grounding analysis, and we do a god-awful job of it. It's really a problem. And I think the community is beginning to understand that. So I think with that, I'll leave you my contact information. Thanks for your patience and for sitting through the noise. And I'll take a few questions, I guess. We have a little time.
Hey, Joe, thanks for the talk. Great way in which you brought data and people together. If you project ahead 5 years out, with artificial intelligence starting to become more and more ubiquitous and accessible, do you see AI as an opportunity or as a threat for something like Trifacta?
Oh, it's opportunity, of course. So the way I view sort of AI in a lot of these contexts is as human assist. There's subjective decisions to be made when you're analyzing data, when you're working with these kind of problems. And the more help you can get from computation, not only to remove drudgery, but also perhaps to suggest interesting things you might not have thought of as a human with limited context, the better. And I view the building of the data for that AI, the context layer, the gathering of information as critical to that. I don't believe that these problems are intended to be automated because it's a creative process working with data. So it's sort of like saying, do I view AI as a threat to, I don't know, art? And no, I think it's an augmentation, and that's awesome. Yeah.
Hi. One of the questions I had is more dealing with incorrectly entered data or incorrectly joined data. Is there anything that deals with more of the data cleaning aspect where it can suggest data records that have gone incorrect entries or incorrect data?
Yeah, so I don't want to project too much on the question, but to repeat it back, I think it was around, I'm not even sure I can articulate it, but let me give you some response, I guess. There's many things with data sets where algorithms can make suggestions that are at a scope that we didn't see in the demo. So for example, handling outliers, or doing data imputation, or doing entity recognition and entity resolution. And those are all pieces of a tool like Trifacta as well. I just didn't highlight them in the demo. So they're critical. And I'd point out a lot of them have been studied in this community. The user experience for those can be very tricky, particularly things like entity resolution. Getting a usable interface to override those algorithms, particularly when you have a high cardinality domain, is a very hard problem, actually. So I think there's lots still to be done on how to make those algorithms kind of fail-safe from the user perspective. So I see more work to be done there as well. Yeah, thanks.
Hi, Joe. Really enjoyed your talk. So you talked about human factors in analysis. Have you looked into human factors when it comes to decision and deployment? Because ultimately, to predict human behavior, to influence human behavior is very, very hard. So any comments on looking at those aspects?
Very nice. So if I understand correctly, you're asking about kind of what happens after the analysis in its effect on the real world. I mean, if I had to hypothesize, I'd say that's a problem best dealt with in application-specific domains, and that the right way to go tackle that would be to pick a domain and go relatively deep so you understand the decision space of that user community and what they have to do. The technology I showed you today is very domain independent. I wouldn't try to solve that problem, I think, in a domain independent way myself. And there's certainly a lot of energy around this kind of work in vertical domains. That's great. Yes, I do.
All right, thank you very much for the questions, and let's thank Joe once again. He has a hard stop, and we'll follow up with the questions later then.
Thanks very much. Thanks for having me.